Now, we have been talking about communication cost, assuming that we have a distributed memory machine, where all the nodes have their own memories and we have to communicate. And you might be wondering what communication cost is if we work with processes which are in a shared memory environment. Well, what I can tell you is that the formula is a bit like cut-through routing, because we don't have any milestone links and so on. So it's also the same, but there is a big but here. Because the ratio here between TS and TW is way smaller and variable than, or dynamic if you might say, than in the case of message passing. And the ratio is lower is because they're basically dealing with the same memory, so it's basically transferred bits from one space to another space, right? But the variability comes from a number of facts. That first of all, the programmer has very little control in his program on the memory layout. The memory layout sometimes influences the communication time between two parts of the system. Secondly, you have caches. So the finite cache sizes can lead to thrashing rate. That sometimes things do not fit in cache, so we have to go back to the main memory, and we get a number of these things, and this causes non-deterministic, sometimes non-deterministic overhead times. Also, there are overheads for invalidate and update protocols, and they're very difficult to quantify in simple models in these cases. Fourth point is that the spatial locality in the cache is difficult to model. You can do it a little bit, but one cache is different than the other cache, and also the cache layers have a large influence, and that there's a lot of variety between various microprocessors, right? Various chips. If you really boil down to, I recently read a paper on what was it? Compare the cost statements you need for atomic control for enforcing atomicity, right? And they had a new protocol for which should be more efficient than the classical ones, but if they analyze the results then on various systems, then you have to go deep down into the cache hierarchy and how do they deal with all the things that matter, that influence the performance of this compare and set. Test and set and compare and swap. Now compare and swap instruction, which is the basic instruction that takes care of the appropriate locking for variables for enforcing atomicity, which you need in some systems. And also, compilers might do prefetching of data. And, who knows what's going on in the compiler? Tell me. Already happy that it issues good error instructions. There was a very funny, but it's a completely sideline. There's an update on iOS, right, at the moment, and they apparently had a bug. Some people, Apple is very fussy about it, but they discovered what it was. It was actually something very stupid, like two go-to statements in a row, just one after the other, without they had an indentation, but not the delimiter character. So it was a useless statement pointing to dead code, right? And normally this doesn't hurt, dead code. Nobody uses dead code, but a man in the middle could use that for an SSL attack in that specific case. So you see that the omittance of, or just the duplication might be that someone made an error by an editor or something like that. Was not discovered by the GNU compiler and has been there for quite some time as an error in the code. So that's my question: who knows what's going on in the compilers, right? Sometimes you think they discover things which they don't, and then a bug can be in the code for quite some time, and can be not harmless, right? Can harm you as a system vulnerability. Right. And last but not least, also the contention of shared variables is difficult to model. If two processes contend for the same shared variable, this is all something which is don't start to model it because it's too difficult. So the take-home message is it's kind of similar like that with the lower ratio of the constants, but there are all these factors which cause variability and make things difficult to model. On the other hand, if we're talking about communication costs, we're talking about large systems, and they're distributed memory by nature anyway because of the scalability problems we have with shared address-based systems. Right, next phase between sending a message from A to B is routing. Right? Sometimes we have, or most of the times, we have alternative paths we can choose. In routing, we have a notion called distance, and the distance is either minimal, which is that the message always takes the shortest path, or it might be non-minimal, right? It might be that a router says the shortest path is too occupied by other people sending across that path, so we take a different route across the system. So the route selection can be either deterministic, it always takes a unique path, or it's dynamic or adaptive, and that's depending on conditions in the surrounding where the message is being sent to. Well, an example of minimal and deterministic routing, minimal being it always takes the shortest path, and deterministic it always takes the same path, is the XY or E-cube routing algorithm. And I'll show you how E-cube works in a hypercube. Suppose I have a hypercube. This is a simple one, 3D hypercube, and I want to send a message from an arbitrary node to another arbitrary node. How do I do that in that way? So it's minimal and deterministic. Well, I can simply do that by taking the exclusive OR of source and destination bit patterns of the nodes. So I number the nodes here, the binary code. In the hypercube way, I've shown how this is built up. And I do that by taking the exclusive OR. Now, how does that work? Well, suppose I have source 1, 0, 0, so that's this one. And I have destination, this one, 1, 1, 1. Then the exclusive OR is 0, 1, 1, right? And I could start with the least significant bit, meaning that if the XOR is 1, then I have to change dimensions in that plane. Changing dimension means that in this plane is the dimensionality of the lowest bit is 0, and changing dimensionality means that I have to send the message to to a node where the dimension of the least significant bit is 1. Right? Then I take the second bit and I do the same. Right? So here I'm in the plane where the second dimension is 0, so that's this plane. Right? And I have to send it to a plane where the dimension of the second bit is 1, so that is to here. Right? for the third bit, we don't have to do anything because the exclusive OR is 0. So here I have made a minimal and deterministic routing. Now there's one thing you could observe here with this routing scheme. That's a question to you. If you see this, it's clear, right? You can do it. But this is the only, the question is this the only possibility for a minimal and deterministic route? Yes?
Maybe you can go from the most significant.
Yes, that's the first question we have. Why start at the least significant? And what you see in the picture here is that if I would have taken this route, it's the same path, the same distance, right? It's also minimal and also deterministic. And that is exactly what's happening if you go the other way around. Right? Starting with the most significant bit. So the same, you start with the most significant bit. The first one you don't do anything. Then you hit this one, meaning that the plane you have to go through is this way. And then you have the last one, and the last one is going down. Right? So that is E-cube routing. It's why routing is in the book. It's kind of similar, but then in a two-dimensional plane. So you can see that also routing can be quite easy, right, in systems like this. And just based on the source and destination addresses. So there is an elegant scheme, at least, where with very little overhead to be able to route messages, right? Because the XOR function of two addresses is about the most simple binary function you can imagine. Right. The next thing is the issue of mapping. Now we have talked about an interconnection architecture like this. For instance, I have here 9 nodes connected in a mesh way without wraparound. But what about my program? Right? My program might look like this. That I have also 9 components in my program, say processes or something like that. And they communicate in this pattern. And what you see is exactly the same. Right? Pure coincidence, of course, in this case, but nevertheless, this frequently happens, right? That I have a program where I have these kind of communication structures. Right? Now, the obvious, the most intuitive way to map this program on this interconnection architecture would be this, right? You probably agree on that. Because then the physical layer aligns with the program layer, right? So this is a very... Now, what would happen if I do something wrong? Yeah?
Overhead on the communication.
Yes, overhead on the communication, and it's very simple to achieve that. The only thing I'm going to do is to switch the mapping of these 2 corners. Twist them around. And if you do that, what you see is that you get this mapping of communication to physical system. And you see immediately that here on this physical link you have 3 program layers mapped onto, right? So this link is way busier than this link where you only have one-to-one communication. So it matters that your program structure is nicely mapped on the underlying network architecture. So mapping is how can I map a programmatic structure, for instance, onto a physical structure in a kind of nice and elegant way, and how can I do that? That's the topic of the next few slides. And if we look at this more abstractly, it's about embedding of graphs. So I have a source graph, and I have a destination graph, G prime, and I have to map the source node and edges to the nodes and edges of the destination graph. That's the thing I did with the previous example. Yeah.
I think a bit more right would be to say that it's also weighted.
That it?
It's a weighted graph.
A weighted graph, yes, of course, it's a weighted graph. It depends on the thickness, but for ease of reasoning, right, we kind of make it homogeneous to see what's happening. What can happen is that we have to map in, if we talk about G, and we go to G prime, we can have congestion, meaning that two channels in the source graph must be mapped on one destination, one link in the destination graph, and that was the last example where some of the physical links have three layers on top of them of the communication channels, right? So that's a clear case of congestion or causing congestion. I also might have this case in the mapping that I have a single line between in the source graph, but I have to split it in two consecutive lines in the destination graph, and then we talk about dilation in graph sense. And that happens less in our problem. We have to split the node into the source graph into two nodes of the destination graph, but this is only theoretical because that doesn't appear in our example, and we call that expansion. Now let's go through some prototypical examples of this kind of embedding. Suppose our program, for sake, has a linear structure, and our system has a hypercube. Right? So our program has a structure like a linear array. So we have a number of processes communicating like this, right? In a linear way. How can I elegantly map that on a hypercube system? Well, I can do it like this. So for sake of simplicity, we take the size of the linear array equal to the dimensionality of the hypercube, right? So we have 2 to the power d linear array and a d-dimensional hypercube, and we have a numbering of our linear array, say 0, 1, 2, 3, 4, 5, 6, and we need to find a function g which map this index given a certain dimension of the hypercube. Can we do that? Well, the answer is yes, we can. Such a function g exists, and I'm going to give it to you. It looks like this. You see? Complex function, it's recursive, right? It has a few starting values. So you say, what's this? This looks complicated, right? In fact, it's a functional description of a coding scheme which is called the reflected gray color. And it's astonishingly simple, despite the complexity of the formula. So how does it work? Well, we start with a linear array of, we start with 0 and 1. Right? What we do is, if we go to a higher dimensionality, copy this one and mirror this one. So we mirror this pattern along this axis. So 0, 1 becomes here, we add 1, 0. And then we append 0 to the top half and 1s to the bottom. Now we go on. We duplicate this one. We mirror it. And we add zeros and we add 1s. That's the recipe what this formula actually describes. Despite its complication, it's extremely simple. If you visualize this, is oh yeah, this is simple. And what you get is a numbering of 8 places here, which is in a different order than the normal order of 0, 1, 2, 3, 4, 5. So if I have a numbering of a linear array of 0, 1, 2, 3, 4, 5, 6, 7, I get 0, 1, 3, 2, 6, 7, 5, 4 in the hypercube. Now, how does that look like? It looks like this. Right? So I start with 0, 0, and I lay my linear array like that in the hypercube. Right? Like a snake. I put it along the edges of the hypercube. In this case, the dilation is 1 and the congestion is also 1. And because one link of the linear array is exactly 1 link in the hypercube. There's something else you can see if you see this. Yeah.
There are some unused songs.
They're all unused links.
Yeah, but
Yeah. It's no wonder, right? Because
yeah, it's illegal.
the hypercube has much more communication capacity than is required for a linear array. So it should be able to process our program, which looks like that, very elegantly, right, without any problems. And of course, it's very easy to mix this up by having a mapping which causes the messages to go through the hypercube all the time. Right? Instead of assigning these two together, assigning them in a way that the next one should be here, then because the message has to pass 3 paths there as well. So in that sense, you have to be careful. We can extend that in a very simple way. Now, suppose we do not have a linear array, but we have a mesh, 2-dimensional mesh, with dimensions. To make it easy, of course, this complexity analysis always makes things easy, that the dimensionality of the mesh is 2 to the power r times 2 to the power s, and we're talking about an r plus s dimensional hypercube. Well, the prescription is very simple, because then I have a tuple, ij, in the mesh, and I just can map it to the hypercube by making the individual grade code functions for I and j, this one on the dimension r and this one on the dimensionality s, and just concatenate the 2 bit patterns. And then I hit my mapping. Right? So it's also possible to map a mesh with dilation N1 and congestion 1 to the hypercube system. So also for meshes to hypercubes, there is a relatively simple recipe to do well. And that's also no wonder, because in terms of power, the power of the interconnection structure, the hypercube is more powerful than the mesh. Right? It contains more links than a mesh structure. So that should be easy. course, we can might be confronted also with the other way around. We have a mesh. Our program now is not a linear array, but it has this two-dimensional mesh structure. But I'm a poor guy, and I almost only be able to say to my boss to afford a linear array of processors, right, that communicate directly between the nearest neighbors. Now then you get the inverse process. You start with a mesh. Yeah, I have to impose a linear array on the mesh, and I could do it like this, right? The linear array on the mesh lay down like this. And I could say, well, this is about the best I can do. And what I get then is this, right? And you immediately see that it's not congestion free, because for one physical link from the linear array, I get here 3 links of my program structure. Now, how bad can that be? In this case, it's even that the congestion might be 4, right? 1, 2, 3, 4. In this case, it's for this link 3, but for this case, congestion is 4. Well, the other way around, it was 1. Well, how bad can it be? We can derive a lower bound on this structure. The lower bound on the congestion, G prime, is the bisection width of G. You can see it by here that in the best case, what I have is that I only have to map the links which I cut here to a link here, basically. So that's a lower bound on the congestion of this mapping. It's not a favorable solution, of course, if I have a more intensive program structure which requires this more intense communication, that I have a kind of handicapped hardware structure underneath of a linear array which is confronted with this overhead. In that sense, you could say my program structure doesn't reflect my hardware capabilities. Another item is a trade-off we have to make between cost and performance. Now, how do we weight these things against each other in terms of, because your boss might ask you what is the cost-performance ratio of your solution, and then with a number of alternatives. Well, suppose our cost is the number of wires, right? So this is our criterion. That's if I buy a machine, then I can calculate that it's approximately proportional to the number of wires I have to install, but I'm not sure about the interconnection structure yet. And we compare the case of a 2D torus and a hypercube. So 2D torus is a linear 2D array. With these wraparound connections, right? And also here. That's a 2D torus. What we do know is that the number of wires, if for the same dimensionality P, that the number of wires in a hypercube divided by the numbers of wires in the torus is P log P divided by 2. And here it's 2P, so that's log P divided by 4. What does that mean? That for one wire in the hypercube we can have, in terms of costs, log P divided by 4 wires in the mesh. Right? I can buy log P times log P divided by 4 times wires for the mesh for the same cost. Now the average distance in the mesh is the square root of p divided by 2, and in the average distance in the hypercube is log p divided by 2, so that's midway in the average cost. Right? So the communication cost, if I take CT routing, is here the number of links, which is here the average number of links plus MTW, and here it's the average links for the mesh. But here I have to multiply the M times TW by this constant, because I can have more wires and hence more throughput for a single link. Right? Now, if I do an order analysis, I get that the communication cost of my system is proportional to M times TW. And here I have 4 times M times TW divided by log P. Now, which one is the better choice? Yeah?
Depends on the number of processors we have available.
Well, yes.
But complexity-wise, if you stretch the 4, then the lower one would be more useful than the CPU.
This one is better, right? In terms, if my number of processors grows, then this one has a lower communication complexity for the same amount of money I spend, right? So this is the winner. If M is large and P is larger than 16, say we can kind of conclude, to our surprise, that our mesh with cut-through routing is more cost-effective in terms of communication cost, which is contradictory to what you would expect, right? So the choice for the tourists is not such a bad choice after all, compared to the hypercube. Right? All these advantages of the hypercube kind of disappear if we take this model. Now you could say this is not realistic. Suppose cost is number of wires. Right? Well, you might take a different argument then, right? Because what is strong in the hypercube is this enormous bisection network, right? Now, cost is bisection network. Right? Well, we can 2D torus versus hypercube. The number of wires in the bisection of the hypercube versus the number of wires in the bisection of a 2D torus is the square root of p divided by 4. And we do the same thing. So it's for 1 wire in the hypercube in the bisection, we have the square root of p times divided by 4 wires in the mesh. In the bisection. Again, average distance is the same. And we come with C2 routing to a similar kind of argument, right, with the same fill-in structure. And instead of log p, we have square. It's not as good as the other one, but it's still better. So also, according to this argument, we see that the torus, the 2D dimensional array torus structure is the better choice here with cut-through routing, right? So the cut-through routing scheme kind of amalgamates the disadvantages of an interconnection structure that at first sight is less favorable to the ideal and optimal properties of the hypercube. But in reality it's not. So, and that is probably one of the reasons that in later systems people adopted more for the two-dimensional torus systems, because cut-through routing kind of got rid of all the disadvantages you had of the mesh versus the hypercube. And by this kind of reasoning, you see why. if we compare them against one each other, is that for meshes its construction is easy, right? It's two-dimensional, it's regular. It also is that a mesh, if we look at an application structure, is a kind of natural mapping from the application, the program structure, to your hardware. Right? It's because you see we look at it later, but and I will give some examples. Also, this two-dimensional structure, maybe three-dimensional, but dominantly two-dimensional kind of decomposition of your application is a quite natural decomposition. As I said, the CT routing diminishes the effective light diameter, and as I said, there are commercial applications. The hypercubes are more important from a theoretical side, is in the fastest hypercube algorithm asymptotically approaches the fastest PRAM algorithm. So it's a good comparison on how good your algorithms are. Also, trees and meshes map easily on an hypercube, and it has an elegant recursive structure. But in terms of building, it's somewhat less elegant, right? If you go to higher dimensional structures, it becomes a nightmare of crosses, because it has to be built in our living space, which is Euclidean, and it's not mathematical, right? So building a hypercube of dimension 10, then I can hardly draw it. I mean, you can draw it, but you get a lot of wires on your paper, and if you draw it in a bit unhandy way, you cannot see how it's composed either. Right, so there's a good break. 5 minutes before time, and we convene next week with basic communication pattern.